Hi, I'm Sriram and I'm going to talk about the design document of my project, that is the journal file system. This design document has been organized into three sections as per the specifications. The first is the purpose of the project, then I have described the high level entities, and finally a brief description of each entity and the design principles. In the design principles, I would explain the various choices that are available for designing the system and also a rationale as to why I chose one design principle over the other. So, first, let me talk about the purpose of the project. So, as we can see, the project implements a journal file system using the two types of atomicity, all or nothing and before or after. So all or nothing is used to enable a file system, or in fact any system, to recover from certain types of faults such as hardware faults and environmental faults such as power outages that may disrupt the normal functioning of the system. So in this atomicity, it deals with multi-step processes where either a process executes all its multiple steps or it backs off from the execution of the process. So it would not, the all or nothing design principle would not allow the system to execute any transaction partially. So the assumptions that I have made that are enlisted in this document, and the system would be used by entities who require fault tolerance and semantics, such as airline reservation systems and banks. So, an airline reservation system, as we discussed in class, it's a classic example where two concurrent clients would request for a service to make a reservation, and clearly it calls for the use of before or after a technique. And in banks, we would surely need the all or nothing as well as the before or after technique. We need the all or nothing technique because if a transaction is occurring, say we are transferring some money from account A to account B, which is a multi-step process, we wouldn't, the customers wouldn't like it if the transaction executed just partially and due to some power outage or any other external factors the system reached an unfavorable state. So for instance, we wouldn't want that the money was credited into an account but it was not debited from the account. The bank wouldn't want that, and similarly the customer wouldn't want that it was debited from his account but was not credited to the receiver's account. So these are just two examples where these atomic principles could be used, but anywhere where we need fault tolerance and atomicity, we could use the all or nothing and before or after semantics in the underlying file systems. And sure, as we discussed in class, the atomicity principles should ideally be implemented in all levels, straight from the physical level at the disk and other hardware to other layers such as the file system where I am implementing this project, and higher subsystems that leverage on the file system such as database and distributed networks. The scope of the project is limited to the file system. So next we move on to section 2. Here I would first discuss about the system architecture. So sorry, in this system, as discussed in the project description specifications, there would be a set of scripts, a set of programs known as the file system script, and these are the various programs that will access the file system. Uh, these programs include all the test cases that execute the system including the faulty prefixed programs as well that deliberately try to introduce errors in the system to verify that the atomicity semantics are running. These scripts access an interface called the file system that would listen to the application or the user requirements, and they would execute the various actions as highlighted in the textbook. This system architecture was designed based on the textbook. The actions include the new action, the read current value, the write current value, commit, and abort. The former three are used to either read a value from the system or write a value into the system. And the commit and abort provide record storage, outcome record semantics. Now the journal system provides a container to uh, reside the journal storage manager and the self storage system. The journal storage manager acts something like a wrapper that listens to the 5 types of requests as shown in the left, and these are translated into system level calls which would be handed into the self storage system. The self storage system would implement the various calls on the low level subsystem, which include the write, the system write, system read, alloc, and dealloc to receive and free memory in the heap, respectively. Apart from that, the self storage system also catalogs versions and stores outcome records. Next, I would discuss about the state transitions. So, the allowed state transitions of an outcome record as based on the textbook is like first, there would be no executing processes. So when a new or all or nothing action is created, it would be first assigned a pending state, and data would be written into the self storage as explained in the architecture. And once the data is ready to be stored in persistence, it would either commit, or if there occurred a failure where we need to recover, it would go to an aborted state. And in either case, the outcome record state is no more of our interest because the version is either committed in self storage, or if it is aborted, it's reverted. So because of this, the outcome record state is discarded. So these are the allowed state transitions in all or nothing. I have extended these states for before or after. So in my project, I'm planning to implement lock systems. So first, when a new before or after action is created, it would be assigned pending state. So this deals with concurrent systems. So if there exists action that was previously executing, that action would be assigned previous ID, that is the ID minus 1, and the current process would be assigned an ID, and the current process would have to wait as long as the outcome record state of the previous ID is pending, and once it is not pending anymore, it will it will move on to the start state, that is, it would acquire all the resources and the locks that are required. And next it will, once it is completed, it would move to the marked state. In this state, it would release the outcome record lock, and since this before or after action is bootstrapped on all or nothing, the remaining states are similar to all or nothing state transitions. That means from the marked state, it would move to the committed or aborted state as discussed previously, and once it moves to either of these record outcomes, the outcome record state is no longer of interest. so it's discarded. Next, I would explain the ER diagram. This is how I explained how the modules and are connected with each other. So this is in compliance with the uh, system architecture. So as outlined earlier in the system architecture, the test environment programs, which include the faulty as well as the regular programs, as well as the multi-threading, they trigger an action which would be either of the five cases, that is new action, read current value, write new value, commit or abort. And these actions are listened by the journal storage manager, and this acts as an interface to the before or after systems as well as the all or nothing subsystem. So as discussed earlier, the before or after subsystem is bootstrapped from the all or nothing subsystem, that is, it's built upon as a layer over the all or nothing subsystem. The either of these both are the atomic semantics, and either of them consult the lock manager before permitting a new action to execute. And these subsystems respectively contain the cell storage system, and uh, the cell storage system executes the low level system calls the read, write, alloc and dealloc as explained in the earlier cases. So next I would explain the use case diagram. So the main users are, the primary users are the client application and the journal storage manager. And the client application places requests for read and write respectively, and these are handled and accepted by the journal storage manager. The journal storage manager forwards these requests as system calls to the cell storage system, and the cell storage system handles the reads, writes, and also allocates and deallocates memory as they are needed. This is the overall sequence diagram of the system. So whenever a new action is triggered, the new outcome records are placed in the atomicity subsystem, and the journaling system manager handles the new request and forwards it to the cell storage. The cell storage would catalog the record state as pending and returns the status back to the file system. The read call places a read current value action on the journaling system manager, which forwards a read request to the cell storage. The cell storage reviews the version history and returns the most recent committed version, and the outcome records are sent as data to file system after ignoring the aborted and committed outcomes. Whenever a write call is done, the new version of the data object is passed as parameter, and these form the tentative value for new version ID of the all or nothing system. The journaling system manager forwards the write request to the cell storage, which places a request to the low level storage manager. The lower level storage manager is nothing but the C implementation of malloc to allocate space on the heap. Whenever a commit is made, it's forwarded to the journal system manager, and the update version, the version history of the record state is updated to be committed. This state is returned all the way back to the file system. Likewise, whenever an abort is called, it forwards an abort request to the cell storage, and this status is returned to the file system. Next, I've explained the entity description and design principle. So the file system, as explained earlier, it acts as an interface. The journaling storage manager acts accepts the various journal storage calls as outlined. The atomicity subsystem provides the all or nothing and before or after subsystem. The cell storage system translates requests made to the journal system and as reads and writes, besides maintaining catalogs, versions, and outcome records. In the design principles for version history, between version history and logs, uh, the version history technique contiguously stores the updated version and um, it is stored as successive versions of data, and these new versions are located and discarded when they are not needed. Since this technique is simpler to implement compared to logs, I would prefer this. Um, the logs technique provides high performance semantics for fast reads and writes. So whenever a new value is to be written, the log would be stored in the journal storage on non-volatile storage contiguously. So the contiguous writes makes it optimized for fast writes. Whenever similarly, the same write value is written the second time into the volatile cell storage. This process is called install, and the installation of the new data, it would replace the old value of uh, the same data, and this would ensure that there would be exactly one copy of that information on the cell storage at any given time. This would make it simpler to read because the system knows exactly where to read if value has to be read, and this is how the cell storage optimizes for faster reads. For atomicity, the all or nothing system is pretty straightforward. And before or after, there are three techniques, that is the simple serialization, the mark point, and optimistic atomicity. The simple serialization offers a simpler semantics over mark point, so I would be preferring that for implementation. The optimistic atomicity is not preferred because it assumes that no interference would occur between the concurrent processes, which is not the case in our project because we are going to deliberately execute multi-threaded processes that would try to interfere between the concurrent processes. So clearly optimistic atomicity is not the choice. Next, I've explained about the locks. So for any locks, first process would acquire locks, then execute the process and release the locks. I've also explained in a sequence diagram of how locks are taken. So whenever a transaction wants to execute, it would first request for a list of locks. The lock manager would check for which are the free locks in the free locks repository, and this would be returned, and at this point it's called the lock point because the transaction has the list of locks that it needs for the transaction to execute. Whenever a transaction begins, the transaction passes the lock set list to the lock manager. On verifying that all the locks required for the transaction are available, the free locks issues a grant or a deny. Finally, when a commit or abort takes place, the lock manager would release the lock set that was acquired by the transaction. This is how simple locking takes place. In two-phase locking, the transactions do not need to know which locks are to be acquired at the beginning itself. So, as and when a transaction needs resources, it would keep acquiring more locks, and that is the first phase of the two-phase locking. Finally, when the transaction has completed executed, they would the transactions would start releasing all the locks and resources that it had acquired, and this is the second phase of the locking protocol. And even after the lock point, they release the locks only if the transaction is sure that that it would not read that object again. So this concludes with my explanation about the design principles for the journaling system. Thank you.